Hello, everybody, and welcome to Chapter 15. This is Professor Algara with another lecture video for this class, and this video particularly will cover, the remaining of Chapter 15. In case you haven't watched the previous video, we define momentum, impulse, and impact, and that's quite important for you to understand what's coming in this video, which is angular momentum. So, like I said, go back to the video if you need to. If not, then just start watching this one. Let's get started. So first we need to define what angular momentum is. And before I do that, I want you to remember what you had in statics called as moment of the force. You remember that was the force times the distance, and that was going to generate a torque. And we use that to study how structures will work. In this particular one, based on what we defined last week, defined as the mass times the velocity, and as a particle move along a path, some energy will be generated, and that energy is called the momentum, right? So when you have that particle moving about an axis, as you can see here, that is not aligned with that axis, it will generate a torque. And that torque will be generated as the result of moving that energy next amount of distance from that axis, okay? And as you generate that, an angular momentum will be generated, and we will use that as a tool to study more movements, okay? So, but as you know, all these equations come from vectorial forms, and therefore, if we're going to perform cross products of these vectors, we need to use that by using, our matrix, and that matrix has to be, as you can see here, with the I, J, and K, in which you have the position vectors in each one of the axes, and then the energy of this, momentum energy and on each one of those axes. The magnitude of this vector, as you can see, it's calculated as mass velocity times the distance. So there is a relationship between moment of a force, which is what I was telling you at the beginning, force times the distance, and angular momentum, which is what we just defined. And the resultant force acting on a particle is equal to the time rate of change of the particle's linear momentum. Showing the time derivative using the familiar dot. Everybody's familiar with this from the notation of the book. We can prove that the resultant force acting on the particle about O, it's equals to the time rate of change of the particle angular momentum around O. And that's exactly what we are about to prove. But before we prove that, right? I want you to get familiar with all the knowledge behind this equation. So we need to think about a system of particles, as we study this. In this system of particles, we have external forces acting to those particles and some internal forces. If we multiply the distance from our axis to these particles, we will get that each one of those forces internally and externally will cause a moment. Okay? And that's basically what we've studied until now. Well, what is very important for us to remember is that the internal forces, they occur in equal but opposite collinear pairs. And because of that, there's no moment for them because you will have one internal force, and you will have an exact internal force acting on the opposite direction, and that will make that your whole internal forces times the distance will be zero. Okay, so one will subtract the other. So we have a system of particles, as you can see from previous thing, right? From the origin O to the system of the particles, you have a radius, which is the distance, right? And these whole particles, we have a resultant external force as a capital F and a resultant internal force as lower capital F. And if we do that, what we need to do is to demonstrate that the sum of all the moments of the force is equals to the time change of angular momentum. For us to do that, we just have to remember what we learned last week, which is the sum of forces, it's equals to a regular linear momentum, right? Which is the mass times velocity. If we multiply this by the distance on both sides, I will get that sum of F times that distance will be equals to r and v, right? And if we rewrite this equation, I have to remember that the moment of a force, it's equals to force times the distance. The sum of all the moments will be equals to the sum of all external forces times that distance. Since we're talking about vectors, it's the cross product, right? So the sum of moments about O will be equals to R cross product mv. And what we need to demonstrate here is a relationship between these two as h o dot it's equals to r, and sorry, this is the time of v, so r cross product mv. Okay, if we want to demonstrate that, it's very simple, guys. Ho dot is the time change or the derivative of linear momentum, right? Is the time change or the derivative respect to the time of angular momentum. In order for me to perform the derivative, I will have to do this by parts. So if I do this by part, I will have that this is equals to the time derivative of the first element, cross product, because we're talking about vectors again, and b plus the value of this cross product m and the time derivative of b. And what we will do, we will take this element and work it through a little bit. So r dot cross product and v. Remember from previous chapter, the v, it's also the time change of the position. So if we take that into this equation, I will get that this is equals to r dot cross product m r dot. And if I take the mass, since it's a constant outside, I will get that this is equals to r dot cross product of r dot. And this is when the theory comes in handy, because the cross product of a vector with itself, it's what? Zero. And therefore, this whole element, it's zero. And what I get at the end is that h o dot, it's equals to r cross product n in the change of b, which is exactly what we wanted to demonstrate at the beginning, right here. So therefore, it is demonstrated that the sum of all the moments about O will be equals to the change of the angular momentum. All right. I hope it clarified the doubts, but again, if you have more questions, do not hesitate to send me an email and I can help you out one-on-one. All right. Principle of angular momentum and impulse. This is very similar to the principle of kinetic and potential energy, or the principle of impulse and momentum that we studied in the previous chapter. Considering the relationship between moment and time rate of change of angular momentum as we just developed in the previous slide, by integrating on both sides with the time interval, I will get that the sum of forces of the moment, right, or the integral of those moments will be equals to h2 minus h1, being this the angular momentum at the end and the angular momentum at the beginning, because we're integrating from t1 to t2 on time interval. Don't forget that. So this element right here can, this whole equation can be written as the angular momentum at the beginning plus all of these moments, it's equal to the angular momentum at the end. What we need to know is that this term right here, it's what we define as angular impulse. Is all of these forces that are causing torque to our system. This equation is referred to as the principle of angular impulse and momentum. The second term on the left, which is this one right here, it's called angular impulse. In cases of 2D motion, it can be applied as an scalar equation using components about the z-axis. And for us to determine that, we will do an exercise. We talked before about conservation of kinetic energy and conservation of momentum. So now we're going to talk about the conservation of angular momentum. When we don't have forces causing impulse, which means we have no forces causing torque, the angular momentum is conserved between T1 and T2. And that's what you need to know. Basically, if you have something as you can see here in the picture, right, there is no, this force, since it's pointing to the center, is not causing any torque, and therefore the angular momentum is conserved in both states, the first one and the second one. I want to now cover everything that we have learned with an example, okay, as I always do in these kind of videos. So two identical 10 kilograms spheres are attached to the rod which rotates in the plane of the page. So it's rotating around O. You know, that axis is pointing towards outside of the page. The spheres are subjected to tangential forces of P equals 10 newtons, and the rod is subjected to a coupled moment equals to AT, where T is in second. We need to calculate the speed of the spheres at T equals 4 seconds if the system starts from rest. Okay, so right now we're in chapter 15. We cover all the statics and we cover close to 4 chapters in dynamics. So you have a lot of knowledge in your head right now, and you need to learn how to use the equations that you have learned until now with the proper knowledge. Like I told you in the last video, assumptions with knowledge in your hand. So you were given with a moment, with a couple moment right here. And you were also given with P. And you also have this that is rotating. You have particles that have momentum and they are located x distance from an axis. And because of that, they're causing angular momentum. So the best assumption for you, since you have a couple moment, is to use the equation that relates angular impulse and angular momentum. Okay, so how do we do that? So we have forces that are causing angular impulse as they generate torque from here to here, right? You also have a couple moment that is being exerted on the rod. And even more so, you have information about the beginning, which is V1 equals 0, which means the angular momentum at the first one is 0. You need to calculate the velocity at the end, and you can use that by relating this whole impulse, angular impulse, to that angular moment. Let's just do that with numbers, and hopefully it'll make sense for all of us. So like I said, for me the equation is very straightforward. Angular momentum at 1 plus all of these integrals of the moments, from t1 to t2, or as we call it, angular impulse, dt will be equals to the angular momentum at the end. Okay, this one, since it starts from 0, it will be 0, and this one right here will have the moment that was given, which is the couple moment, and also the moment that is generated by P. And then HO2 will be equals to the mass velocity at the end, which is what we're looking for, times the distance. Okay, so let's just start throwing some numbers. These sum of forces, sum of moments, right, will be all of the different forces that are causing moment. So the first one that we have, obviously, it's the integral of the couple moment given by the rod, which is AT dt, and these go from 0 to 4. Then we have the integral from 0 to 4 of P, which is 10, times the distance, which is 0.5. And more importantly, don't forget that you have two spheres, so that has to be multiplied by 2. And then this is all equals to the mass, which is 10 kilograms. Yeah, that's what was given, times velocity, and the distance of those 10 kilograms from O will be 0.5. And more importantly, don't forget to multiply this by 2 because we have two spheres. So as we develop this equation, we have 4 that multiplies 4 to the square. And then right here we have 2 that multiplies 5 and 4. And then this is equals to 10b. If we solve for b, we will get that v it's equals to 10 0.4 meters per second. Straightforward, and we got the velocity. Those exercises are usually very straightforward. I guess the dynamics of these exercises is that you need to know what you have in hand, and that way you can set up a plan. Remember, as I always say, it's a puzzle, it's a big puzzle. You have different pieces, you have to put the pieces together and solve what is needed. And with this, we have concluded chapter number 15. This video and the previous video all together will be chapter 15. As I told you, it was going to be a short video just to kind of finish up the chapter. This content is very important and it will be in your exam. So thank you very much for watching. Let me know if you have any questions. Thank you.